we have supervised and unsupervised learning. Okay. And what is the peculiarity of supervised data? Our data, supervised learning, the data will be like this. What is this? X equal to X comma Y. There will be a set of features and each data point is mapped into a particular label too, right? But in the case of unsupervised learning, we don't have such kind of labels. Okay. And here there is a fact, this X is always a subset of what? R raised to N. X is always a subset of R raised to N. And what about Y? What about Y? If Y is equal to C1, C2, etc. up to CK, a set of discrete labels, then we call it as what?
Classification.
Classification. Otherwise, Y is again a subset of what?
R.
Real number set, that it is called as
Regression.
regression. And in classification, our motive, what is our motive? Motive is to find a mapping phi from X to Y, right? So that we can predict Y cap from unknown input X cap. Is it clear? And what is the criteria for this? What is the criteria for this? What is the criteria for selecting this? There are a lot of functions, right? There are a lot of possibilities for mapping X to Y. And what is the app file?
It can map the input data into the output classes.
Output classes with phi is equal to minimum or phi cap is equal to minimum phi, right? Where y minus phi of x മനസ്സിലായോ?
അതായത് എറർ കുറവായിരിക്കണം എന്നല്ലേ ഈ പറഞ്ഞതിന്റെ അർത്ഥം?
അതായത് ഈ ഒരു നൊട്ടേഷൻ എപ്പോഴും ഓർത്ത് വെക്കുക. This is a very important notation.
Can
Okay.
you repeat, sir?
Yes. Yeah. So, as I said, if you consider this phi, it could be any function, right? Let's say if our data is 1 to 1, 2 to 4, 3 to 9, 4 to 15.9, and 5 to 25.2. Okay. You can have phi as what? Phi of x is equal to, it can be x square. Phi of x can be x square minus 0.1. Phi of x is equal to x square plus 0.1. Phi of x is equal to x minus 1 whole square. Phi of x is x minus 0.1. Phi of x is equal to x plus 0.1 whole square. Okay. So these are all different possibilities, right? Are you getting that? Are you getting that? These are all different possibilities, right? So it can be considered as a set, right? Set of all functions apt for phi. And which one I can choose? While choosing phi, we have to minimize this quantity. So for each of this particular phi, you will get a different value for sigma y minus phi of x, right? For each of this, you have different value for this, right? Is it clear? And among all these possibilities, one which give minimum error, one which give minimum error can be the ideal classifier, ideal mapping, and that is the ideal classifier. Is that clear? Are you getting that?
Method of least squares അല്ലേ?
അത് എറർ ക്യാൻ ബി അതുകൊണ്ടാണ് ഞാൻ സ്ക്വയർ ഒന്നും ഇടാത്ത. എറർ ക്യാൻ ബി ഡിഫറെന്റ് ഫങ്ഷൻസ്. ലീ സ്ക്വയർസ് തന്നെ ആകണമെന്നില്ല. അത് നമ്മളിപ്പോ അത് വി ആർ ആക്ച്വലി ഗോയിങ് ടു ദിസ്. ഇറ്റ് ക്യാൻ ബി വെറുതെ ഒരു ഈ മോഡ് സിഗ്മ വൈ മൈനസ് ഫൈ ഓഫ് എക്സിനെ വേണമെങ്കിൽ എനിക്ക് എങ്ങനെ ഡിഫൈൻ ചെയ്യാം? സിഗ്മ മോഡ് വൈ മൈനസ് ഫൈ ഓഫ് എക്സ് എന്ന് ഡിഫൈൻ ചെയ്യാം. അല്ലെങ്കിൽ സിഗ്മ വൈ മൈനസ് മോഡ് എക്സ് ഹോൾ സ്ക്വയർ എന്നുള്ള രീതി എടുക്കാം. അതിൻ്റെ സ്ക്വയർ റൂട്ട് എടുക്കാം. അല്ലെങ്കിൽ ഐ ക്യാൻ ടേക്ക് ദി തേർഡ് റൂട്ട് അല്ല ഫോർത്ത് റൂട്ട് then y minus phi of x whole cube എടുക്കാം. പിന്നെ പലതരത്തിൽ we can actually calculate the loss. In different ways we can actually calculate the loss. That could be anything, but and this should be error. Somehow we are calculating the error. And while calculating the error, one function which gives the minimum error can be chosen as the ideal classification model. Is it clear?
Actually, this explanation works for numerical data, right? For example, as I mentioned, when we classify galaxies, we are having different images.
Yeah.
At the time, do we have to go for this kind of functions?
Yes, there also we are having features, right? And each classifier is actually mapping into a particular class. ഒരു ക്ലാസ്സിലേക്കല്ലേ മാപ്പ് ചെയ്യണേ? Then there will be a predicted class and a actual class. Predicted class and an actual class, right? And that predicted class and actual class can be used to this y is the predicted class. Okay. This y is the actual class, and phi of x will be the predicted class. Right, in the case of classification, this y will be the actual class value, and this phi of x will be the predicted class value. So one sample is can be like y and phi of x. So there are 5 people, 3 with not corona, 5 with corona, and I'm calculating the predictions as no, y, 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 y. Okay. So if you consider this no as 0 and y as 1, 0, 0, 0, 1, 1, 1, 0, 0, 0, 1, 1, 1, 1. So what is the total loss for this prediction? Can be calculated, right? Error equal to, what is that? 0 minus 0 whole square plus 0 minus 0 whole square plus 1 minus 0 whole square plus 1 minus 1 whole square. So you will get an error of 1 for this data. പക്ഷേ ഇപ്പോ if this is also 0, what will happen? This is also 0 ആണെങ്കിൽ ഒരിടത്തൊരു 0 minus 1 whole square കൂടി വരത്തില്ലേ? So the error will be 1 plus 1 is equal to 2. Apo some phi 1 is actually giving the previous result and some phi 2 is actually giving another result like 0, 0, 1, 1, 1, 1, which is giving minimum error. Is it phi 1 or phi 2? ഈ കേസിലെ ടോട്ടൽ എറർ എത്രയാവുന്നത്? 2. കാര്യം there are 2 mismatches, right?
Yes.
ഇവിടെയോ? Only 1 mismatch. So the total error is only 1.
1.
So which one we can choose?
Phi 2.
Phi 2 can be choose. Is it clear? Clear ആയോ? Right? For everyone? Is it clear?
Yes, sir.
Yes? Okay. So I think we can start, right? So ഇങ്ങനെയുള്ള ഈ കുറേ ഫൈകൾ, what all ways we can build such kind of files? We are actually going to discuss that. Okay? That is what is happening in different classification methods. Okay. Yeah. So is the screen visible now?
Yes, sir.
Yes. So, as I said, machine learning enables system to learn from data and improve without being explicitly programmed, right? And within machine learning, we have supervised, unsupervised, and reinforcement learning. And within the supervised, we have classification and regression. And particularly in supervised learning, as we said, a model learns from past labeled data and make predictions on new unseen inputs, right? So usually we have a labeled data, then we are model training on giving a new data, it will give the prediction. And that supervised learning can be defined like classification if predict a discrete label, regression if it predicts a continuous value. Is that clear? Is it clear? Right?
Yes.
And in this lecture, we are actually going to discuss about how logistic regression, support vector machines, k-nearest neighbor, naive Bayes, and decision tree classifiers are working on classification. So first, we are starting with logistic regression. Okay, logistic regression. So logistic regression is a supervised classification algorithm that model the probability that an output X belongs to a given class using a sigmoid function, right? So in regression, what we are doing is we will directly find a particular linear model, okay, a linear function to map a set of values, right? So in logistic regression, as even it is a regression, we are using it for classification purpose. Okay. And how can we model this? How can we do this? Okay. So that is what we are going to discuss here. So to explain this, I am simply taking a data. Okay. Is the screen visible to you?
Yes, sir.
So see, suppose my data are like 1, comma 2, right? 2, comma 4, 3, comma 6, 4, comma 8, and 5, comma 10. One more data I can put. Again, 6, comma 12. Okay. If you observe this data over here, leave it as shown. Ah, yes. See, if you observe this data, you can see a data like this, right? Okay, എല്ലാവർക്കും everyone is actually understanding this, right? Yeah. And what is happening in regression? We assume that y is equal to wx
2x.
plus theta or wx plus c, right? And what we will do? We will adjust the value of w and c, right? So that the area we are getting, oh sorry, the error we are getting is some kind of very minimum. Is that clear? Is that clear?
Yes, sir.
Yes? Yeah. So for a regression purpose, even if the data is slightly like 4.2 or this is 4.1, 5.8, ഇങ്ങനെയൊക്കെ ആണെങ്കിൽ കൂടി, even if the data is like this, what will happen? We can actually reduce the error, right? So what is the need of this, or how we can actually find this? So can we understand this problem? With the given set of x and y's, right? 1, 2, 2 for 0.2, 3, 6, 4, 1.8, 5, 10, and 5.8, 12. Okay. We are trying to find out an appropriate y equal to wx plus theta or wx plus b, right? And what do you mean by finding a appropriate wx plus y? An appropriate w and b, right? In such a way that 2 minus w into 1 plus b square plus 4.2 minus w into 2 plus b plus, right, 6 minus w into 3 plus b, so on, 5.8 minus w into 12.
It's to 12 now.
Yeah. Right? This quantity is actually can also be, this is the total error, right? And this total error can be represented as this sigma yi minus w into xi minus b whole square, right? Is it clear? Are you getting it? Confusion ഉണ്ടോ ആർക്കെങ്കിലും ഈ എഴുതിയതില്?
No, sir.
So the last quantity is 5.8, no?
5.8. 5.8
Or
minus.
12.
Sorry. It's 12
This
minus.
12 now.
Yeah, it's 12 minus. This is 5.8. Yeah, exactly. Yeah. So this is what we are calling as total error, right? And this is called as an error function. This error function is actually depends on what all variables. This yi and xi are fixed values, right? So these are all, this error function is depending on what? W and B. Is it clear? W and B. And what are the choices for W and B? What are the choices for W and B? What are the choices from W and B? W can be any real number, right? And B can also be a real number, right? So together this ordered pair, WB will be an element of what? R square, right? So we have to find a W and B element of R square, which gives minimum on what? This S of WB. That is nothing but minimum WB from R square, which gives root of sigma yi minus wxi minus b the whole square. Is that clear? And that ideal w and b is w cap, b cap. This is the problem of regression. And to find this w and b cap in linear regression, we have two equations. With the help of the two equations, we can find it out, right? But what is the another approach we can do? See, since this S is actually depending on W and B, this is a multivariate function, right? Are you getting it? It's a multivariate function. And its domain we can choose a value for W and we can choose a value for what? B2, right? And based on each value for W and B, you will get an error value S, right? Is it clear? Error value S. So what will happen? These error values are actually
സാർ
giving
ഇവിടെ
us a
ഡബ്ല്യു ബി ഒരു കോൺസ്റ്റന്റ് ആയിരിക്കില്ലേ നമ്മൾ സെലക്ട് ചെയ്ത് അവസാനം കഴിഞ്ഞു കഴിഞ്ഞാൽ
എല്ലാം കഴിയുമ്പോൾ
ഡിഫറെന്റ്
കോൺസ്റ്റന്റ് ആയിരിക്കും. But for that constant, we have different possibilities, right?
ഓക്കെ 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 അതിൽ മിനിമം എടുക്കാനായിരിക്കും അല്ലെങ്കിൽ ഒപ്റ്റിമം എടുക്കാനായിരിക്കും.
അതെ. So there are different possibilities in with the different possibilities. What I have to do? I need to find a pair of WB, which is giving W cap and B cap, right? Which have minimum value for this S, which is having minimum value for this S. And how can we find this? How can we find this?
Can we use that gradient descent?
Exactly. This is why we have learned gradient descent. And in gradient descent, what we have discussed, if you have such a function represented by a surface, then we can randomly start from a point. We can randomly start from a point. We can jump and jump and jump and jump and jump. Finally, we can arrive at what? W cap and B cap. Is it clear? Are you getting it? Hope this is fine, right, everyone? Okay. This is how we are using this gradient descent for regression. So if we don't have that regression equation, namka beta 0 and beta 1, if we don't have an equation, then we can make use of this gradient descent for the purpose. Okay, fine. Now, when it comes to screen visible alla, poile.
Yes, sir.
Yes. So when it comes to another kind of data, as I am having 6 observations, and the first 3 observations, okay, first 3 observations are actually representing zero comma 0, 1, comma 0, and 2, comma 0. And the next set of observations are, I'm plotting it as 2 colors because this represents 2 classes, right? Four comma 1 and 5 comma 1. Okay, like, is it clear for everyone? Is this clear for everyone?
Mm,
Yeah.
I didn't understand these two. Are you having two sets of data?
I have total 6 data, and the first 3 data is having the features 0, 1, and 2, but they are all mapped to one class 0, and the other 3 values are having the feature values 3, 4, and 5, and they are mapped to a class label 1. So you can interpret this data in this way: X and the corresponding class. X is 1, 2, 3, 4, 5, 6, and the classes are 0, 0, 0, 1, 1, 1. Clear? Is it clear?
Uh, for example, if we have done that assignment where we were classifying in the first case, ഒരു leaves അല്ലേ ഒരു set of
Yeah.
leaves തന്നില്ലേ
Maybe
so
the radius of a particular leaf.
yes and then the same feature for the same feature you are having two different values, right?
No. What is the same feature? Here
No,
the
what
features
I'm
are
asking is
1 to...
petal size. If suppose you have petal size as one
Mm,
feature, that
mm.
petal size is different for different classes.
Yeah.
So in that case, for the same feature, you are having different values.
Yes. For the same feature, I have 1, 2, and 3, 4, 5, and 6. Maybe you can think like this
Okay,
is the
okay,
radius of the
okay,
flowers. And there are
okay,
2 type of radius of the leaves, and there are 2 types of leaves. So
okay, okay,
one category of leaves are always having a radius less than 3, and the other category of leaves are actually having a radius greater than 3. So
okay.
these are all class 1 leaves, and these are all class 2 leaves, right? So suppose we are getting another leaf to 0.8. This is the radius, whether it is 0 or 1. This is our problem. Is it clear?
Yes, sir.
Yeah. So as we are having y is equal to wx plus wx plus b here. However, you can adjust this, but this will not give an appropriate approximation of the power level. Even if you do like this, can we say this is a good approximation?
Couldn't understand this. Why you need this? You're
To,
already having two different classes, right?
yeah, so to know about the distribution of this data, is this line properly give, a prediction? Because if you give 0, this will predict like 1 minus 1 point, what is this line? the line could be minus 0.3 plus 0.3, right? So the line's equation is, if you do this as an approximation,
You're trying to draw a line which is classifying this data into two.
yeah, which is classifying the data into two. So I'm trying to approximate this using a line, and that line I'm getting is, see, y is equal to, okay, right, 0.3 x plus minus 0.3, right? So if you substitute a 0 here, what will be my prediction? So these are all 0, 1, 2, 3. Sorry. These values are 0, 1, 2, 3, 4, and 5. If you substitute 0, the class is 0. Instead, you are getting what? 0 minus 0.3, right? And again, if you substitute 1, it will be 0. So you substitute 2, it will be 0.3. If you substitute 3, it will be 0.6. If you substitute 4, it will be 0.9. If you substitute 5, it will be 0.9, it will be 1.2, right? So if you calculate the error, 0 minus minus 1.3, 0 minus 0, 0 minus 0.3, this error will be very high, right? Because this is not properly classifying our data, right? So taking a linear function for approximating this kind of data is a wrong choice. That is what I am trying to say. You cannot consider a line like this for approximating the behavior of data here. So instead of taking this, okay, instead of taking this, I'm taking another function, okay. That function is something like z is equal to 1 by, okay, 1 plus e raised to minus y. Okay. So this y I am intending here is this. So I'm simply pasting this equation over here. And I'm taking it as what? Y. And this y is actually nothing but what? Wx plus b. Right? Now, see what is happening if I change b and w. See? See? What is happening here? On choosing B as minus 25 and W as 10, what is the values predicted by this function? Are you getting my point? Instead of simply taking y is equal to wx plus b, I am taking another function 1 by 1 plus e raised to minus wx plus b. And this function is actually called as a sigmoid function. What is that? Sigmoid function. So whatever integer value you got for wx plus b, it will be simply mapped into either 1 or 0 over here, right? So what about the predictions?
സാർ ആ കോൺസെപ്റ്റ് ഒന്നുകൂടി പറയുമോ? അതായത് 1 or 0 എന്ന് പറയുന്നത് രണ്ട് തരം ക്ലാസ്സേ ഉണ്ടാവുള്ളൂ എന്നുള്ളതിലാണോ?
അതെ, ബൈനറി ക്ലാസിഫിക്കേഷൻ ആയതുകൊണ്ട്
classification output is 0 and 1, right? So that's
Yeah.
what we are trying to
Yeah,
do
the
here.
classification,
Okay.
because the data we are having, see, the data we are having is like this, right?
0 and 1.
0, 1, 2, 3, 4, 5. And for this classes, the output is 0 for these 3 observations and 1 for these 3 observations, right? So according to this is our x and this is our y. And what is y cap? Y cap is nothing but 1 by 1 plus e raised to minus, okay, e raised to minus, what is that? 10x plus 25. So if you substitute the x value 0 over this equation, what is the mapping? What is the mapping here? For 0, what is the y? It's 0. For 1, 0. For 2, it's 0. For 3, it's 1. For 4, it's 1. And for 5, it's 1. What is the total error?
0.
Error, right? So appropriately, we need to find the value of w comma
B
theta,
അല്ലേ?
w comma b as what? 10 comma minus 25. Provided this error must be minimum. And what is the rule we are taking here? We consider this point. Okay. So suppose you put 2.7. I have asked for that, right? If you put 2.3, what will be the mapping? 2.3 will be somewhere this side. If you put 2.3 over here, it will be somewhere this point, right? So what we are doing is, see, we will consider this point, that is 0.5. And this point we will take as a decision boundary, because this particular B is responsible for this shift, okay? And this W is actually responsible for this. The curvy nature, right? So here, for 3, for 2 and 3, we are not exactly getting mapped to 0 or 1, right? Are you getting it? For this case, the 3 is not exactly what?
Is not
1,
exactly 1. It's
1,
near 1.
near 1. And for 2, it is not exactly 0, 2,
0.
right? So, we can say that after finding such a decision boundary, if this function, that is y is equal to 1 by 1 plus e raised to minus 10 plus this function is actually giving a value greater than 0.5, then it can be mapped into class 0. Sorry, it can be mapped to class 1. Otherwise, that is 1 by 1 plus e raised to minus wx plus b is greater than 0.5. We can say it is class 1. If it is less than 0.5, we can say it is class 0. Are you getting my logic?
Yes, sir. Actually, but
Yes.
the first
Yeah.
intuition will be to use a step function instead of the sigmoid function,
Yeah.
right?
Yes. But step
Uh,
function will make a big errors. It won't actually consider the, as I said, if the flavor is having 2.35 or 3.2 or 2.9 kind of observations, that step function will make big errors, right? In the edge cases. You consider like this is what we are asking, right? The step function.
Yes, sir.
Yeah, that will make a big errors. So instead, we can actually smoothen it so that instead of a crisp value, we can say that every value in between 0 to 1, right? Every value is actually having in between 0 to 1. So we can say that logistic regression is actually predicting a probability for being towards a class. And the probability is greater than 0.5. This will belongs to class 1. Otherwise, it belongs to class 0. Is that clear?
Yes,
Are you
sir.
getting? Yes. So ultimately, the logistic regression is giving a probability. Okay. The logistic regression is actually giving a probability. And to maximize this probability, we have to appropriately find what? W and B. Okay. So with this, we can actually now understand the concept. Hope the illustration went well, right? We can do this slides. Yeah. See? So instead of predicting a direct value, it predicts a probability, okay, y equal to 1 given x, which is equal to a sigmoid value of z. And z is nothing but w transpose of x plus b. And this sigmoid function or logistic function is mapping every output mapped by this z in between 0 to 1. And the decision rule is that if sigmoid is having a greater than 0.5 value, that belongs to class 1, and otherwise it belongs to class 0. And this is actually called as a threshold. So the threshold is 0.5. Then what will happen? If it is greater than threshold, it belongs to class 1. Otherwise, it belongs to class 0. Right? And the property of sigmoid is that the sigmoid will map any values into 0 as it belongs to as it tends to minus infinity, and the sigmoid is mapping to 1 as it tends to positive infinity. Okay, so whether this function or whether this particular error, that comparing 0 minus 0 whole square, 0 minus 1 whole square, is that appropriate for a classification problem? Okay, is that appropriate for a classification problem? So there we say that that particular thing is not apt, that mean squared error or root mean squared error or Manhattan distance or whatever it is, this is not appropriate for a classification problem as an error value. So instead, we consider this particular binary cross entropy. Okay, binary cross entropy as a error value. So for different values of W and B, we calculate what a value called binary cross entropy, and this binary cross entropy is nothing but the actual value into log of predicted probability plus 1 minus actual value into log of 1 minus predicted probability, right? And this particular term will give, see, I can show you some mapping. So the predicted values, see, yi and pi. The values are 0, 1, 2, 3. Or I can say it as 0, 0, 1, 1. The probabilities are, it is 0.
നമ്മൾ സിഗ്മോയിഡ് എടുത്ത ആ വാല്യൂസ് തന്നെയാണോ സാറ് കൺസിഡർ ചെയ്യുന്നത്?
ഇത് actual, this is the actual labels.
രണ്ടും കുറച്ചൊന്നേ ഉള്ളൂ അല്ലെ? 0, 1, 2, 3 വേറെ എടുത്തു അല്ലെ? ക്ലാസ് വേറെ ക്ലാസ്സിലേക്ക്.
അതെ, ഇത് രണ്ട് ക്ലാസ്.
ഓക്കെ.
Okay. Now, this is the actual labels. This is xi, this is yi, and this is pi. Now, if we calculate the probability, what is it? As per the equation, yi is 0 into log 0, right? Plus 1 into log 1. Okay. Clear, right? And here, yi is 0 into log 0.3 plus 1 into log 0.7. Here it is 1 into log 0.8 plus 0 into log 0.2. Here 1 into log 1, right? Plus 0 into log 0. Okay, right?
Nice.
So 0, just think about this. What are the values for this? This is 0, right?
Yes.
And this is log 0.7. Log 0.7.
Minus 0.35.
Minus 0.35. And what about this? Log 0.8.
Minus 0.22.
0.822 ആണോ? Minus 0.9.
Minus 0.22, I think.
Log
Natural
0.8.
log അല്ലേ? Natural log അല്ലേ എടുക്കണ്ടേ? അതോ log to the base 10 ആണോ?
ഏതായാലും കുഴപ്പമില്ല. അത് പ്രൊപ്പോർഷണൽ അല്ലേ?
Natural log minus 0.22.
നേരത്തെ -0.35 പറഞ്ഞത് നാച്ചുറൽ ലോഗ് ആയിരുന്നോ?
Yes.
.22. Okay. Right.
അല്ല അതെ 0.8 ആണല്ലോ, ശരിയാ. മറ്റടുത്ത് 1 - y into log 1 - pi അല്ലേ?
അതെ. Right, and here it is again 0, right? See, just think about this. Are we having big error in predicting 0 as 0?
No.
No, sir.
So the error is 0, right? Are we having predicting 1 as 1? Are we having a big error in predicting 1 as 1?
No.
No.
So we got an error of 0, right? And what about the error in predicting 0 as 0.3? This is 0.3 unit change, right? And what about 1 as 0.2? Which is having more error? Is the first case or the second case?
First case.
First case. So we got a value of what? 0.35 for the first case, 0.22 for the second case, right? Are you getting it? So this function is a perfect one for calculating errors if we have a binary classification problem and predicted probabilities. Hope you are getting this, right? So instead of taking simply y minus y cap the whole square, we are taking this as a loss function. And this function is called as log loss or binary loss entropy. മനസ്സിലാവുന്നുണ്ടോ? Is that clear?
ലാസ്റ്റ് പറഞ്ഞ സാർ ഒന്നുകൂടെ പറയാമോ?
Yeah, instead of taking y minus y cap, okay, instead of taking y minus y cap as a loss, it is better to have this function as a loss function. Okay, see, and you can see the loss surface.
There's a doubt. Actually, what is this P? Is it the value
Probability.
that the sigmoid function that gives you?
Yes, sigmoid of wx plus b. That is P.
That means the error is shown in the region between that
0 to 1.
that's about the threshold value, right?
Yes. 0.5 is the threshold value, as the probability being 1 is getting decreased, or probability being 0 is getting increased. That is moving towards 0.5, the error will be high. So why we are actually going for this? If you look into, see, MSC, if you calculate an error surface, okay, calculate an error surface, it will be having multiple local minima and maxima, right? But if you model that error as a cross entropy or a log surface or a log error, it is having a convex shape, then it is always easy to find out the minimum. Are you getting my point?
This is about the classification problems or logistic regression.
Yeah, that is for classification problem. If we consider this MSC as a loss, the error surface we are getting will be like this. It will have local minima, local maxima, multiple maximum and minimum points. But here we have only one local minima.
So are we applying this loss function for all classification models?
Exactly. All classification models, we use this log function as used as a error function. Is it clear?
Yes, sir.
Everyone?
ഒന്നുകൂടി പറയാവോ? എല്ലാ ക്ലാസിഫിക്കേഷനും ഇത് തന്നെ ആയിരിക്കും എറർ, അങ്ങനെയാണോ പറഞ്ഞത് നമ്മള്?
എല്ലാ ക്ലാസിഫിക്കേഷൻ മോഡൽസിനും ഇപ്പൊ നമ്മള് ന്യൂറൽ നെറ്റ്വർക്ക് എടുത്താലും സപ്പോർട്ട് വെക്ടർ മെഷീൻ എടുത്താലും ഈ ലോജിസ്റ്റിക് റിഗ്രഷൻ ഒക്കെ എടുത്താലും ലോസ് കാൽക്കുലേറ്റ് ചെയ്യാൻ, ബൈനറി ക്ലാസിഫിക്കേഷൻ ആണെങ്കിൽ ലോസ് കാൽക്കുലേറ്റ് ചെയ്യാൻ എപ്പോഴും നല്ലത് ഏതായിരിക്കും? ഈ ബൈനറി ക്രോസ് എൻട്രോപ്പി ഫംഗ്ഷൻ ആയിരിക്കും.
അത് ഈ മറ്റേതിന് നമ്മളിങ്ങനെ കുറെ ലോക്കൽ മാക്സിമാസ് അല്ലെങ്കിൽ മിനിമാസ് വരുന്നത് കൊണ്ട് നമ്മൾ ഇത് എടുക്കുന്നു, അങ്ങനെയാണോ?
അതെ അതെ അതെ. നമുക്ക് ആകെ മാപ്പ് ചെയ്യേണ്ടത് ഐദർ 0 or 1 അല്ലേ ഉള്ളൂ. ഐദർ 0 or 1ലേക്ക് മാപ്പ് ചെയ്യേണ്ടത് കൊണ്ട് ഇവിടെ ഒരിക്കലും നമുക്കൊരു സ്മൂത്ത് കർവ് കിട്ടില്ല. ബട്ട് ദാറ്റ് സ്മൂത്ത് കർവ് ക്യാൻ ബി generated using this binary cross entropy. Okay.
It's easy to apply the gradient descent here.
ഇവിടെ gradient descent അപ്ലൈ ചെയ്താൽ എളുപ്പമാണ്. പക്ഷെ ഇവിടെ നമ്മൾ അപ്ലൈ ചെയ്ത് കഴിഞ്ഞാൽ ചിലപ്പോൾ ഈ പോയിന്റ് നമ്മൾ സ്റ്റാർട്ട് ചെയ്ത് കഴിഞ്ഞാൽ we will get stuck at a particular local minima. അവിടെ നമുക്ക് എന്ത് ചെയ്യാൻ പറ്റില്ല, ചാടി പുറത്തു വരാനായിട്ട് പറ്റില്ല. Okay. Hope this is fine, right? So find, അപ്പോൾ എന്താണ് ലോജിസ്റ്റിക് റിഗ്രഷനിൽ നടക്കുന്നതെന്ന് മനസ്സിലായല്ലോ. With a given set of data, we have to find an appropriate value for W and B. Okay, W and B. And what is happening? Finally, if there is a new point comes, we substitute that into the equation of 1 by 1 plus e raised to W transpose X plus B. And if you are getting a value greater than 0.5, that belongs to class 1. Otherwise, it belongs to class 0. And for multiple classes, okay, for multiple classes, what we will do is, we will consider, see, നമുക്കിപ്പോൾ ഒരു മൾട്ടിപ്പിൾ ക്ലാസ്സസ് ഉള്ള കേസ് ആണെങ്കിൽ, say suppose we are having ഓക്കെ, ഇങ്ങനെ 3 ക്ലാസ് ഉണ്ടെന്നിരിക്കട്ടെ. അപ്പൊ ഇപ്പൊ പറഞ്ഞ പോലെ നമ്മൾ എങ്ങനെയാ ചെയ്യാ? How we can apply this? What we will do is, we will find 1 W transpose X plus B by taking one class as positive and all other classes negative. You will also find another W transpose X plus B, maybe the W1, B1 and W2, B2, and also we will find another line W3 transpose X plus B3, right? So what you are getting is, you are getting 3 decision boundaries, right? 3 decision boundaries, right? So what we will do, we will calculate the probability of a new X0 on this particular decision boundary on this decision boundary and on this decision boundary. And ഇതിൽ ചെയ്യുമ്പോൾ നമുക്ക് 0.5 കിട്ടുന്നു എന്നിരിക്കട്ടെ. And ഇതിൽ ചെയ്യുമ്പോൾ we are getting a value of 0.7 and this is giving a 0.9. Right? So what we will choose? That x belongs to this particular minus. ഇത് നമ്മൾ 0.9 ആയിട്ടും ബാക്കിയുള്ളത് എന്താ എടുത്തിരിക്കണേ 0.1 പ്രോബബിലിറ്റി ആണ്. റൈറ്റ്? So we will consider that particular sample belongs to this minus. Is that clear?
സർ ഇവിടെ ഇത് പിന്നെ മൾട്ടിപ്പിൾ ക്ലാസ്സസ് വരുമ്പോൾ അത് ബൈനറി ആക്കി കൺവേർട്ട് ചെയ്യാനാണോ ഇങ്ങനെ?
അതായത് മൾട്ടിപ്പിൾ ക്ലാസ്സസ് വരുമ്പോൾ നമ്മൾ സാധാരണ ചെയ്യുന്നത് 1 വേഴ്സസ് റെസ്റ്റ് എന്ന് പറയുന്ന ഒരു സ്ട്രാറ്റജിയാണ്. അതായത് ഒരു ക്ലാസ്സിന് നമുക്ക് വേണ്ട ഇൻട്രസ്റ്റ് ഉള്ള ക്ലാസ്സിനെ നമ്മൾ എന്ത് ചെയ്യും പോസിറ്റീവായിട്ട് എടുക്കും, ബാക്കിയുള്ളതിനെല്ലാം നെഗറ്റീവ് ആക്കും. അപ്പോൾ ഒരു ഡിസിഷൻ ബൗണ്ടറി ഈ ക്ലാസ് പോസിറ്റീവും ബാക്കിയെല്ലാം നെഗറ്റീവായിട്ടായിരിക്കും. ഒരു ഡിസിഷൻ ബൗണ്ടറി ഈ ക്ലാസ് പോസിറ്റീവും ബാക്കിയെല്ലാം നെഗറ്റീവായിട്ടായിരിക്കും. ഒരു ഡിസിഷൻ ബൗണ്ടറി ഇത് പോസിറ്റീവും ബാക്കിയെല്ലാം നെഗറ്റീവായിട്ടായിരിക്കും. ഓക്കെ അല്ലേ?
Okay.
Again, there is a confusion because instead of taking linear equation, we opted sigmoid function earlier, right?
Yeah.
And now we are again going for linear.
അല്ലല്ല, ഇത് ലീനിയർ അല്ല മാം. ഇത് ഞാൻ പറഞ്ഞത് ഈ മോഡൽ ചെയ്ത് കഴിഞ്ഞാൽ ഫൈനലി ദ വാല്യൂ ഇസ് ക്രിയേറ്റഡ് യൂസിങ് ദിസ് ഇക്വേഷൻ. ഈവൻ ദോ വി ആർ മാപ്പിംഗ് ഇറ്റ് വിത്ത് e raised to minus ഇങ്ങനെ 1+ ആണെങ്കിൽ പോലും അൾട്ടിമേറ്റ്ലി നമുക്ക് ഈ ഡബ്ല്യൂയും ബിയും കണ്ടുപിടിച്ചാൽ പോരെ.
So you are finding out the sigmoid function which is fitting the data, then using that W and B to find the linear line.
Yes. അത് ആ ഡബ്ല്യു ആൻഡ് ബി ഒരു ലീനിയർ സെപ്പറേഷൻ ആണല്ലോ ശരിക്കും.
Okay.
Ultimately ഇത് നോൺ ലീനിയർലി ആണ് പോകുന്നത്. But for the ease of representation, I just make this as a decision boundary. You can think like this. ഇങ്ങനെയുള്ള ഒരു സിഗ്മോയിഡ് വരാം. ഓക്കെ, അങ്ങനെ നോൺ ലീനിയർ ബൗണ്ടറീസ് ആയിരിക്കും എക്സാക്ട്ലി അത്. ബട്ട് ഫോർ ദ സേക്ക് ഓഫ് റെപ്രസെന്റിങ് ദി 1 വേഴ്സസ് റെസ്റ്റ് ഞാൻ അതങ്ങനെ 3 പറഞ്ഞ.
The sigmoid is already having a linear part. So is it
ആ ലീനിയർ പാർട്ട് ഞാൻ അവിടെ റെപ്രസെന്റ് ചെയ്തേ ഉള്ളൂ. ആ ലീനിയർ വാല്യൂവിനെ നമ്മൾ 0 to 1 മാപ്പ് ചെയ്യാനാണല്ലോ സിഗ്മോയിഡ് ആക്കുന്നത്. So the data is actually created with separated with a linear line. Then we are mapping that data points to a probability value between 0 to 1. അപ്പൊ ബൗണ്ടറി കണ്ടുപിടിക്കുമ്പോൾ നമ്മൾ ഒരു ക്ലാസ്സും ബാക്കിയുള്ള എല്ലാ എലമെന്റ്സും വേറൊരു ക്ലാസ്സും, അടുത്ത ക്ലാസ്സും ബാക്കിയുള്ള എല്ലാ ക്ലാസ്സും വേറൊരു ക്ലാസ്സും, അങ്ങനെ 3 ക്ലാസ് ഉണ്ടെങ്കിൽ each will take as positive class and the rest of them will consider as negative class. So similarly for 3 classes we can have 3 decision boundaries, and on applying a new data set on these 3 decision boundaries, one decision boundary will give a high probability towards a class. അതായിരിക്കും നമ്മൾ എന്തായിട്ട് എടുക്കുക ടാർഗറ്റ് ആയിട്ട് കൺസിഡർ ചെയ്യുക. Is it clear?
അല്ല, എനിക്ക് പെട്ടെന്ന് ബിക്കോസ് ഈ ഡേറ്റ വെച്ച് നമ്മൾ ഇഫ് യു ആർ ഫിറ്റിംഗ് ദ സിഗ്മോയിഡ്, I am feeling the other way that you are drawing a sigmoid like this and this linear line will become complementary to the linear part in sigmoid. That is what I feel. I don't know.
Ultimately മാം ഇതിപ്പോ നമ്മൾ നേരത്തെ കാണിച്ച ഒരു ഫീച്ചറും ഒരു ഇതുമല്ലേ കാണിച്ചേ, ഒരു ടാർഗറ്റും അല്ലേ കാണിച്ചേ?
Yes.
ഇവിടെ നമുക്ക് 2 ഫീച്ചർ ഉണ്ട്. ആ ടാർഗറ്റ് എന്ന് പറയുന്നത് ആക്ച്വലി കളർ വെച്ചിട്ടാണ് റെപ്രസെന്റ് ചെയ്തിരിക്കുന്നത്. ഈ സിമ്പൽ വെച്ചിട്ടല്ലേ നമ്മൾ ടാർഗറ്റിനെ റെപ്രസെന്റ് ചെയ്തിരിക്കുന്നത്?
Yes.
അപ്പോൾ ആക്ച്വലി ഇതൊരു 3-dimensional ഡേറ്റയാണ്.
Okay.
Some of the points will be distributed over here and some of the points will be distributed over here. ഇവിടുത്തെ ഡിസിഷൻ ബൗണ്ടറി എന്ന് പറയുന്നത് തന്നെ എങ്ങനെ വരും അറിയോ? ഇറ്റ് വിൽ ബി ലൈക്ക് ദിസ്. ഒരു ആ ലൈൻ തന്നെ ഒരു പ്ലെയിൻ ആയിട്ട് കടന്നു വന്ന എങ്ങനെ ഇരിക്കും? ആ പ്ലെയിനിന്റെ മുകളിലും താഴെയായിരിക്കും. Sigmoid in 2D.
Okay. Okay.
Sigmoid in 2D നമ്മൾ നോക്കിക്കഴിഞ്ഞാൽ we can actually understand that. Sigmoid 3D space. ഇത് കണ്ടോ? It will be a curve like this. ഈ കർവിന്റെ മുകളിലും താഴെയായിരിക്കും. ഓക്കെ അല്ലേ?
Okay, sir.
Some data points will be on this point and some data points will be on this region. അങ്ങനെയായിരിക്കും ഇത് വരാം. Okay. So hope logistic regression is clear for you, right? Is everyone? Can you just put a response on the chat box whether this logistic regression is okay or not? Yeah. So next we are trying to understand another classification method which is called as support vector machine. So a support vector machine is again a classification algorithm which finds a linear hyperplane. Okay, which finds a linear hyperplane. So ഇവിടെ വേറെ നോൺ ലീനിയാരിറ്റിയുടെ കൺഫ്യൂഷൻ ഒന്നുമില്ല. ആസ് വി ആർ ഹാവിങ് some data like this and some data like this. Ultimately, what we need to do is we need to find a hyperplane like this, which is in the form of W transpose X. Okay, or W dot X. We are finding a what? Hyperplane over here. Then, if you substitute a point over this region, what will happen? If you substitute a point here, W transpose X, then it will be less than 0. A point on this region, it will be W transpose X greater than 0. So for any classification, we can actually find a hyperplane that separates two class of objects. Is that clear? Are you getting it? Right? And this is what happening with a neural network that we are going to discuss. But the thing is, if you have a data like this, okay. So is this the right hyperplane? Or is this the right hyperplane? Because see, if we label this as girls, okay, and the features are like height, and weight. So girls are having less height and less weight, and these are boys. Boys are having more weight and height. Okay. And if there is a new observation appears over here, okay, with this blue hyperplane, I could say that observation is a boy, right? But this with green hyperplane, I can say this is a girl. So which hyperplane is correct? So there will be n number of hyperplanes, right? These are all different possibilities for a hyperplane. Are you getting my point?
We have both the test training and testing data. So the minimum error, based on that, we can choose the hyperplane.
So how many hyperplanes we will iterate or we will enumerate? There's n chances for having a hyperplane, right? By slightly changing each
Yes,
W and
angle.
beta. Yeah.
Yes.
There will be different kind of hyperplanes, right? So all these hyperplanes which classify the data properly can be a right hyperplane, right? But this is not an optimal hyperplane. What is that? The optimal hyperplane. Okay. So all these things in the figure, this is a hyperplane, this is a hyperplane, this is a hyperplane. All these things are about hyperplanes. They are all right hyperplanes too. But we couldn't say all these hyperplanes are optimal. Okay. So in support vector machine, what we are focusing is that instead of finding a hyperplane, a simple right hyperplane, we are trying to find an optimal hyperplane. Got it? മനസ്സിലായോ?
ഈ
And what
ഒപ്റ്റിമൽ ഹൈപ്പർപ്ലെയിൻ എന്ന് പറഞ്ഞാൽ മാക്സിമം ഇതാണോ?
അത് നമ്മൾ പറയാൻ പോവാം. Then the question arises, what is the idea for optimal hyperplane? See, this is one illustration like the female candidates and the male candidates. See, these are the decision boundaries with different decision boundaries. So there are points which can classify our data properly, but that need not to be a optimal hyperplane. So what do you mean by optimal hyperplane? The optimal hyperplane is nothing but we will consider some points in the data set. Okay. Like suppose we have data like this. And some points. Okay. So if you look at this data, you can actually find some data points which are nearer to our boundaries, right? Is it clear? Which are nearer to our boundaries. And these observations are called as support vectors. What is that? Support vectors. Then what we are doing is we consider a hyperplane. Okay. We consider a hyperplane. Then parallel to that hyperplane through support vectors, we will find out two lines right? We will find out through lines, and the distance between these two lines is actually called as what? Margin. What is that? Margins. Okay. So these are marginal boundaries or marginal planes, and these marginal planes is actually parallel to our what? Decision boundary, and the distance between these marginal planes is actually what? Marginal distance. So if you consider another hyperplane, see, another hyperplane like this, so if you consider another hyperplane like this, then the margins are like this, right? So which distance is higher? Is it blue or magenta? Is this blue or magenta?
Blue.
Blue, right? So likewise, some hyperplane is there which is having a maximum margin. Is it clear? Some hyperplane is there, that is the hyperplane W transpose X is there, which gives this the optimal hyperplane. Okay, it's optimal hyperplane which has maximum margin, and that hyperplane is actually calculated in support vector machine algorithm. Is it clear now? Till that point, the hyperplane that maximizes the margin is actually called as optimal hyperplane, and that hyperplane is calculated in support vector machine. And see, even though there are different cases, see here both A and B separate the class correctly, B has a higher margin. So നമ്മൾ ഇവിടുത്തെ optimal choice ആയിട്ട് ആരെ എടുക്കുക? We consider as B. And if there are presence of outliers, we will simply ignore it. Okay, we will simply ignore it. Okay, and what happens if the data is non-linear? See, if this is non-linear data, right? Or I can make a more understandable way, like, see, if this is our data axis and this is our one set of observations, and this is our another set of observations. Clear alle? This is our another set of observations, and this data is particularly described using how many features? Can anyone tell me how many features? How many features are there in this? Therefore, this particular data?
2.
Yes, there are 2 features, X and Y. And with this X and Y, we are clear that this is not linearly separable. Will you be able to find a line over here?
No.
But what we are doing is we will introduce a third feature, Z is equal to X square plus Y square. We will introduce a third feature which is equal to X square plus Y square. So suppose the points are -1, 1, 1, 1, 1, -1, -1, -1. If these are the points, and the other set of points are 2, 2, 2, -2, -2, 2, -2, -2. Okay. So what is the value of Z for these 4 points? 1 square plus 1 square, that is 2, 2, 2, 2, right? And for here, it is 2 square plus 2 square, that is 8, 8, 8, 8, right? So what will happen? This value is nothing but, since it is Z equal to X square plus Y square, this is a distance from center to each point, right? Right? So this measure is actually the Z. So what will happen if I plot this data into a 3-dimensional space? Here X and Y is there. Along with that, the new Z is also there. So what will happen? These red points will be appeared like a circle at a height of 2, right? And the blue points will appear like a circle at Z equal to 8. Now, can you tell me whether I am able to find a hyperplane over here?
Yes.
Right? This is called as a kernel trick. What is that? A kernel trick. So, support vector machine assumes that if a problem is not linearly separable at some dimension, it will be linearly separable at some other higher dimension. Is that clear? Is it clear for everyone? And the key behind support vector machine is that it will consider that classification problem, what we are giving, as an optimization problem. And it will identify if it is a nonlinear problem, in what dimension it will be linearly separable, and in that dimension, what is the hyperplane they need to find as a optimal hyperplane. So by solving these 2 things, what will happen? We can actually solve a classification problem which is either linear or non-linear using a kernel trick and by choosing an optimal hyperplane.